Thank you, and thank those who came to this last talk of the conference. You would be free in half an hour or even less. Yeah. And I would present a very basic presentation, very far from this very nice superconducting, unconventional and other magnetism. So I will talk mostly about one of the altermagnetic candidates, manganese 5 silicon 3, and I will tell a head-breaking story how we found, or at least predicted, magnetic structures coming from some phenomenological considerations and Landau type theory of altermagnetism. And the take-home message of my story is that in principle our well-known mean field approach to the magnetic dynamics, like LLG equations, works well in altermagnets also, but we need a little bit tune this approach by introducing some altermagnetic degrees of freedom. So the motivation of this work started when I heard about this altermagnetism, which worked mainly in the electronic sector, so to say. And here at this conference we have seen a lot of these second quantization operators, spin up, spin down, and so on. So everything working with a spin polarization. But then the question coming from the experimentalist, what should we do in the lab when we apply a magnetic field? How would we describe the magnetic dynamics, which at the end is our aim, to manipulate magnetic states and to control them and so on. So the main question which arises, whether we can still use our well-known LLG type approach combined with the Landau theory, mean field theory, to describing magnetic dynamics of altermagnets, or should we develop some brand new theory for this? So we decided to tune these well-known equations, beta evolutions and revolution at this point. And then I start talking about the material, which is an altermagnetic candidate and was presented by Tomasz in his on the first day of the conference. But before I will go to the details of this material, I would like to start from the concept of altermagnetic order parameter, which we suggest here. And the idea is to find a tool which helps us to distinguish between antiferromagnets and altermagnets, and do it in a very efficient way within the phenomenological approaches. So to do this, we started from looking at the way how we describe magnetic phase transition to ferromagnetic and antiferromagnetic phase. And what we usually do, we start from the paramagnetic state. This is the essence of the Landau theory. And then we color the magnetic sublattices and get ferromagnetic or antiferromagnetic state with the corresponding order parameters expressed in terms of sublattice magnetizations. But what can we do for describing the altermagnetic systems? So our idea is not to go in one dimension when we have only this magnetic ordering. We suggest to introduce another dimension in the phase diagram. So let's imagine that we start from some paramagnetic state which has a spherically symmetrical magnetic environment. And then, in principle, we can imagine a kind of transition which prepares a lattice to be an altermagnetic. So no magnetic ordering at all, but there is something which distinguishes these fully symmetric S-type structures from those which would be then altermagnetic. And then we can describe this with the aid of some spherical functions or tensors, but what is important, we introduce these tensors at each side of the future magnetic lattice. And in this way we can get a kind of ferromagnetic, altermagnetic ordering, or altermagnetic, antiferromagnetic, altermagnetic ordering, but in this line the lattice is still non-magnetic. Then we can imagine that we have a transition to the magnetically ordered state. So then we can get a bunch of different structures. And if we are talking about the altermagnetic ordering or altermagnetic phase, then we go through this line, like from virtual imaginary phase, we go to something which has an altermagnetic crystal structure, and then look at the magnetically ordered phase. Or we can even go in this way, so we can imagine that first our lattice became antiferromagnetically ordered, and then it transforms to the altermagnet. Whether this transition is real or imaginary, I don't know, but by introducing this separate order parameter, altermagnetic order parameter, I have a tool which allows me to see what altermagnetism brings into my system compared to the antiferromagnets. And before I go further to the manganese 5 silicon 3, I would like first to thank the first speaker of this session for showing this type of the phase diagram. So what we suggest is something similar to what is here. So because this in phenomenology, the altermagnetic order parameter can be related to the symmetry of the orbitals or to the symmetry of the crystal environment. It does not matter from the point of view of this mean field theory, but in this phase diagram you see that you can go from the antiferromagnetic to altermagnetic phase. You can go to first to the altermagnetic paraphase and then to the altermagnetic phase and so on. So this type of transition in principle can exist. And before I go further, I would like to, before you start asking the questions, which I am always asked, I would like to compare our definition with what was already discussed in, at this conference, and it was introduced by the Dresden group and also by Jörg Schmalian. So this is a Landau paper, 1936. It's a classical definition, and it refers to the order parameter as a kind of probability density, which means that the order parameter is something which we consider as a statistical average of a physically small volume. So it's not a microscopic value, it's macroscopic. And then the recipe is to construct the free energy using this order parameter and then minimize free energy. So this gives you new phases. Sorry. No. The alternative introduction of the order parameter suggested by Paul McCartney is slightly different. So the first difference is that it includes both spin degrees of freedom and space degree of freedom. So it's something which appears already at the transition point, magnetic transition point. Second, it's related with a microscopic parameters. It's not statistically averaged, and it's also considered as a secondary order parameter, which means that it gives only a flavor of these new altermagnetic symmetries. So in the point of the transition from the non-magnetic state to the magnetic state, the transition should be still antiferromagnetic. Yeah? And the other definition was given by Jörg Schmalian. It's also based on the microscopic approach. Yeah? So it's average, but it's quantum average, not statistical average. So our definitions are slightly different. And now I would like to switch to the demonstration how this approach works. And now I will talk about this very complicated material, manganese 5 silicon 3. So sorry if I would be a little bit boring, but there were a lot of questions what is the structure of it and how it's ordered, so I would like to be very clear in this aspect. First, this is a kind of upper view or top view of the lattice of manganese 5 silicon 3, and it has silicon and two types of the manganese atoms, 2 plus and 3 plus, and 2 plus could be magnetically ordered and 3 plus are not magnetically ordered at all. So this means a structure quite complicated because you need to distinguish between blue dots. But what is interesting and important, if I look at the magnetic atoms and I look at the local environment of the magnetic atoms in this lattice, then I see that this environment has a proper symmetry which should give me a G-type altermagnet. And this is a good news. Yeah? So then looks like it's very simple, but it's not the whole story, because the other point that among these two manganese atoms, these manganese 2 plus are also very specific. When the material is magnetically ordered, only 2 of 3 have magnetic moment, and the third one is idle. I cannot explain why, but that it is what it is. So then this means that in principle, in the magnetically ordered state, we can have 2 orange and 2 green, spin up, spin down, so to say, and gray, which are idle. But you can see that this kind of hexagonal structure can be also distributed within the lattice in the different ways. And one way to order these hexagons is shown here. So you can see that along these lines we have like chains of orange, orange, green, green, which means that this type of exchange interactions are antiferromagnetic, and this structure corresponds to the antiferromagnetic case. Though material has a possibility to be a G-type altermagnet, it has proper local symmetry. It's not enough in the real case, because in the bulk material this ordering doubles the unit cell or enlarges, multiplies unit cell 6 times, and then ends up in the antiferromagnetic structure. However, it's also possible to order these hexagons in a different way. So here you see that all hexagons are similar, and then within these lines we have fully ferromagnetic coupling, and within these lines we have fully ferromagnetic coupling. So the difference is in these interactions. And oops, sorry, wrong button. And this phase is altermagnetic phase. This type of ordering can be obtained while you grow material on the buffer, and this is what our Czech group and French group is doing. And in this case, you have this multi-layered structure with a lot of the deformations, which also play an important role. And so this is a altermagnetic candidate. And now I'm switched to the problem of the magnetic structure of this material. So the one feature which distinguishes antiferromagnet from altermagnet is the anomalous Hall effect, which in this case can be measured on the film with a Hall bar, which is oriented so that the hexagonal symmetry axis is perpendicular to the film. So if the material is antiferromagnetic, so no Hall effect. If it's altermagnetic, there is a Hall effect. Nice and good. And then this what we have seen, and this nice lady Mina Levinska, she did a lot of the experiments in which she applied a magnetic field in that direction, and then start rotating it so that it goes through the plane, and did it for different devices which were placed in different crystallographic direction, and you can see that all these, independent of the directions, all the dependencies were very similar. They showed a kind of transition regions, and they showed non-zero signal of anomalous Hall effect. So the conclusion was that probably this is an Altermagnet, but what is its magnetic structure and why it behaves in this way in the magnetic field? So what we needed to do, we needed to reconstruct the magnetic structure from these curves, but in the beginning it seems very difficult. Yeah, please. You have a question?
Oh yeah. What is alpha versus?
Okay, sorry, I did not explain. You mean, okay, alpha is an angle between the whole bar and the crystallographic axis within the plane. So, the real picture of this material is even more complicated than I explained before. This is not the whole story. And the problem is that when you look at this ordering, these two pairs of magnetically ordered atoms, you understand that they could be distributed within this hexagonal in a different way. So I can do it in this way, I can do it in this way, and I can do it in this way. So in reality, I have three variants, like crystallographic variants of the atomic distribution, and on top of this I have 180-degree domains, at least for each of the variant. So if I do my whole bar which covers all three variants, then the signal which I see should be averaged, and it would be very difficult to extract the orientation of the magnetic system with respect to the real crystallographic axis. So here it was a real challenge which was solved by Xavi Rial, who did a very thin electrode, this whole bar. He went down to 0.5 nanometers before this experiment, micrometers. Before this project, I was always very boring when experimentalists discussed how thick or wide this whole bar can be, 3 micrometer or 2.5, what's the matter, what's the difference? But yeah, so here the size matters, and when we went down below 1 micrometer wide of the electrode, we hoped that now we are working with a single variant, and this was he who said it, not me.
How small is it?
Half micrometer. Yeah, we could not go to the smaller, it was so technically, but in this case, the smaller the better. So this is a general picture which we got using these very thin electrodes. And what you can see here is that all the curves are very different, in contrast to the previous slide where all the curves were identical. And the difference between these curves is the orientation of the whole bar with respect to the crystallographic axis. Yeah? So it's schematically shown here. Oh, no. So the difference of these dependencies, it's the same whole bar, but it's a different plane in which I rotate the magnetic field, as shown here. So here the magnetic field is rotated within this plane, here the magnetic field is rotated within this plane, and so on. So 6 different possibilities which should cover this hexagonal, initial hexagonal crystallographic symmetry. So if you look at these curves, first of all, these solid lines is experiment. These thin lines are theoretical fitting. But when you first look at these pictures, they look different, but still they look very noisy. There are a lot of steps, a lot of minor loops. So how to distinguish what is important, what is not? But when you look more attentively, you see that 2 of 4 are very different. This one and this one, which we called the smoking guns. And now I will discuss it a little bit in more details. But before, I would like to show how I introduce this altermagnetic order parameter, so to be clear how the theory was built in this case. So what is shown here is a kind of this magnetic structure of manganese 5 silicon 3, but here I keep only magnetic atoms, one sublattice, other sublattice, and ideal magnetic atom. This is the other layer, and this is simply projection to make the things clear. And in principle, here to try to connect the experiment with the theory, I can try to introduce this altermagnetic order parameter, and this I will do in the way that I first fix one of the magnetic atoms, and then I look at the non-magnetic environment composed of manganese 3 plus and silicon 4 minus atoms, and then construct a kind of such tensors, depending on the distances between the non-magnetic and magnetic atoms. And this procedure I will do for each of the magnetic atoms, and then take a difference which will give me the order parameter. And what is important for me is not the absolute value of this order parameter, because I do not relate it with any microscopic value. What is important is the symmetry of this matrix. What elements are non-zero and what are zero. And this order parameter allows me to construct magnetic energy, effective magnetic energy, which depends on the components of this order parameter, and then it also depends on the magnetic vectors, magnetization and the Néel vector. And what is again very important here is that I see that the Néel vector couples with magnetization, and it couples in different ways, so in plane and out of plane component are mixed. And this is a basis for further phenomenological description of the system. And what is also important, once I have coupling between the Néel vector and magnetization, this means that here could be also magnetic field. It would be some term which depends on the magnetic field, and this also means that anisotropy of this material can be controlled by the magnetic field, and that is why we see a lot of transitions in the experimental dependence. And this is what we modeled theoretically. So what you see here is an energy landscape in 2 angles. So I described the state of the Néel vector with the 2 spherical angles, and you do not need to read it seriously, but what you see here that because of these additional altermagnetic terms, the system has stable and metastable states. So these green states, they have larger energy, but still these are dips in the energy landscape, and in principle the system can up here, but not in the ground state of the system. And if I apply a magnetic field, then this relief changes in different ways. I can eliminate all these metastable states. I can connect them with each other, so I can get different configurations depending on in which direction I apply the magnetic field and varying its value. So we had a tool to calculate equilibrium state of the system, but it was not the whole story, because what we measure anomalous Hall effect, and then to reproduce a magnetic structure from our experimental data, we need to have a coupling between the magnetic structure and what we measure, this anomalous Hall coefficient. And this is, you know, like this Sophocles, who was this Greek philosopher's paradoxes. I have an object and I see only shadows on different walls, and they can give me very, very different projections. So from this I need to reconstruct the object itself. And here it was also the case where this altermagnetic order parameter helped us, because what we did, we modeled not only the free energy, but we also modeled the conductivity or hole resistivity phenomenologically as a function of the magnetic degrees of freedom. And then what we got a standard contribution which depends on the magnetization along the whole vector. In this case, that direction. And nothing new, but magnetization can be small or vanishingly small. But what was important, the theory or the symmetry analysis predicted us that it should be a contribution which is related with a certain component of the Néel vector. And then when I rotate the system, when I apply the magnetic field, this component should change, and this should be reflected in the anomalous Hall effect. So then what we did, then we looked at the curves. Yeah, first of all, this is a comparison of the loop at the field out of plane. So this is a theory, this is a experimental part, and they agree quite well. And the rest of the curves, which I will show, they are taken somewhere here. So the field, the value of the magnetic field is fixed at the saturation, but close to the coercive field, and then the magnetic field is rotated. And then when it's rotated, you can go to this area for certain projections, and then go through different magnetic states. So now I return back to this experimental part. So smoking guns. So what specific pictures among all these do we see? So we see this curve, which is very different from the others, because all these curves have a shoulder at 90 degrees and 270 degrees, and this does not. So I would say that all these curves, they show that the system undergoes transitions through at least 3 states, here, here, and here. And in this case, we have transition only between 2 states, which are separated by 180 degrees. So it was smoking gun number 1. And the other smoking gun was this web type of the dependence. So if you look at these shoulders, they are, and this shoulder is, so something different. Spider, yeah, spider. Yeah, so then we took these 2 angles as a reference point, and then we started simulating the equilibrium orientation of the Néel vector and magnetization separately to find different contributions. So for this kind 2-state system, we found out that this kind of dependence is possible when the magnetic field is rotated in the plane which is exactly perpendicular to the Néel vector. So this plane shows the plane where the magnetic field is rotated, and the color code shows the angle between the magnetic field and z-axis. And here the Néel vector is happy, very happy. For any orientation of the magnetic field, but because we still have small magnetization, if the field is quite large, then it matters whether the Néel vector points in this direction or in this direction. And we see this like switching between 180 degree cases. And then for magnetization, we have a contribution which scales almost like sine cosine, and on top we have this rectangular switching of the Néel vector with a hysteresis loop, which agrees very well with what we see in the experiment. And the other type of dependence is the spider dependence, and this was like starting point of all the project, because when modeling the dependence of the Néel vector, you see that the Néel vector gives you this wrong slope or negative slope of the angular dependencies, which you never get if you look only on the magnetization. And this is because the rotation of the Néel vector is quite complicated, and this type of the dependence appears when the magnetic field is rotated in the plane which includes the equilibrium value, equilibrium orientation of the Néel vector. So this type of dependencies. And then we also look at the slope at this point, because it was like very clear evidence that something happens, so that the contribution of the Néel vector is very important. And we found out that there is like quite a wide range of the angles within the plane between the whole bar and the crystallographic axis, for which this slope will be negative, and this should give us these very strange dependencies. But if we go to the average for the white whole bars, all these effects wipe out, and we have normal slope as is given by the magnetization dependence. And for other orientations of the magnetic field plane, we can get more or less normal curves. So they have a slightly different shoulders. This is because the structure of this energy terms, and this also helped us to extract their numbers so that we could fit all these experimental data in a very consistent way. And this was one sample, so we look at the many samples, and for other samples we figured out that we were very lucky that we have this pronounced spider dependence, because for the other orientation we had a kind of two variants. So one variant gave the main signal, but the other variant also contributed. And here we were able only to see one of these smoking gun curves. But nevertheless, then it's still quite consistent with the theory. And maybe a couple of slides simply to flash what we also can do with this altermagnetic order parameter. So you have seen this type of curves today and during the conference many times. So we did it also based on this phenomenological model, where we introduced additional term. We found additional contribution to the free energy, and it gave us a splitting of the modes. So these red and dark lines show the phenomenological fitting, and we attributed it to the so-called altermagnetic stiffness. So this means that the coupling, exchange coupling between sublattices 1 and 2 within certain directions is different. It is swap if you rotate the system 90 degrees for D wave. So it's also nice result. And for manganese 5 silicon 3, we also can look at the frequency. This is a gap in the spectra as a function of the magnetic field orientation or magnetic field value, and we figured out that in the points where we have this phase transition, we should see softening, and this maybe can be a guidance for the experimentalist to prove or disapprove the suggested magnetic structure. And with this, I'm at the end of my talk. So we demonstrated that the altermagnetic order parameter allows us to describe consistently static states and also magnetic states. And of course, I need to acknowledge all people who contributed into this work. So thank you.
Yeah, so can you go back to the slide where you show how to like write down this order parameter for the like the environment? No, yeah, this one. I didn't really get, so what is the input I have to put in that I know from the system to write down this order parameter?
So what I did here, it's like straightforward. I fix these atoms, then I introduce all the vectors which connect a magnetic atom with a non-magnetic environment. And I construct a kind of tensorial value and sum over all these atoms. And then this gives me a symmetry. For example, if it would be a cubic symmetry, then I will have some non-zero contribution only along Z, X, and Y, and the rest will be, by symmetry, will be cancelled. If I have orthorhombic symmetry, I have non-zero components, as shown here. So, of course, in simple case, you can guess this symmetry, but using this simple approach, you can get it also in the cases when the system is quite complicated, like in this case.
So it's always 3 by 3 because...
No, not always. So if you go to the G wave, then you need to go for the fourth order, for the fourth rank tensor. So it would be like spherical harmonic. I mean, here it's the idea, but I do it systematically. So I try different tensors, and I stop at the first one, which gives me non-trivial components.
Okay.
So if everything would be trivial, then I will go to the next one.
Mm-hmm. Okay. Thanks.
Yes. So I have one question. Technically, maybe you said it. What temperature did you measure these curves?
I think it was like 100K, but I cannot say. So there was also temperature dependence, but we did not analyze it. So it was 80 or 100, something like this.
So, because I think the report in the bulk is that there is another phase transition at lower temperature.
It's film. It's film. It's not a bulk.
I know, but in the bulk.
Yeah, so it was in the film, and it was in the phase which was altermagnetic candidate, and we assume that we have only 2 or 3, because if you go to the lower temperatures, it's more complicated, and I think that also this anomalous Hall signal can disappear.
Yeah. Okay. So the other question I had is, so this is fairly large unit cell, even if it's gamma point ordering, as you say, because so it should be natural to do resonant scattering to look at these reflections, the magnetic reflections. There's obvious experiment, right? So
you mean RIX, or you mean?
No, REX, elastic scattering, just to look at the magnetic reflections.
I mean, I am a theoretician, but then.
No, I know, but I can do the experiment for you if you want. It's very simple. But if I have a large unit cell, you have these soft X-rays, you have Bragg peaks in the Evol sphere, and you can just look at the magnetism. They are as strong as the Bragg peaks of the film. So, because in obviously, yeah, in the bulk, of course the ordering that's been reported is not the gamma point, so it shouldn't have a anomalous effect. So it'd be very simple to distinguish these two from using elastic resonant X-ray scattering.
Okay, good. That looks like a nice conversation over lunch. I think that's all for today, or for the whole week. I wanted to thank Olena.